or as smooth as possible transition between the previous one and the next one, but it's actually a sharp sharp transition, because there is no really there is definitely no convergence on the previous topic. And as you mentioned, Alex, I mean, having decision made on this topic will be, I think, crucial for you, right? Because depending on that, and I don't know how you and Christian are seeing things for this topic.
Really, I want to have a closer look at the code of Adrien. Because the thing for me, there should be a path between the two. It's just that we don't need to stay on our stones. I mean, given where we start, I mean, even if everything is not perfect, it's easy to get improvement. So.
Yeah, definitely. And so Maxime told us that he was going to be able as well to join tomorrow morning. So it could be interesting to have also his feedback. But yeah, looking at the both maybe in Simo repository with this bug matrix writer, I just took the 1 minute, less than 1 minute to look at the first lines of codes, but and as well to Adrien repository hopefully will help a bit.
Yeah, the problem is that just looking at code does not, it helps, but it doesn't give the reason why the developer choose to do that.
I know what we need to look at. What is important for me is how for instance, in the force field, when you receive the matrix, because the idea is then you will receive a matrix because it's an add cat matrix, is not a get cat. So what is the interface, for instance? How complex is this interface? Because today the interface is just ugly and so complex for nothing.
Mm-hmm. And to make the transition now, so can you explain how it will relate to constraint? It's because you're like basically this same kind of because
I think it's much easier for constraint. The problem is for me it's much easier to understand. It's about the matrix, constraint of matrix.
I mean, I mean the relationship between constraint resolution and matrix assembly.
Alex mentioned it a little bit. So today we build matrix for constraints on a specific format. It's a matrix derive, and if we would like to solve a matrix so this constraint in a standard solver, we need to convert them into a sparse matrix format. And the other thing is that we use this matrix derive for actually doing the transfer of stiffness through a mapping. So the operation, Alex. So
basically use it for everything that's rectangular, right?
Yeah. And for me, this matrix derive is a really specific format that we developed in SOFA for our problems, and we should simplify that. In the same way we use matrix assembly. I think it's. I think you already did. We did that, right, in Simo? You remove matrix derive.
No, we still use it like for interaction. Then again, it's just like we change the underlying data structure. So it's I think like in in the public repository, like maintained by the compiler. It's a map of map. So it's storage which is different from the compressed sparse storage. So what we did was to basically have a unique compressed sparse storage for all the sparse matrices, right? Basically. So irrelevant of for us on the type of block that they store. So you have like essentially like symmetric matrices, which are a specific type of compressed matrix, and rectangular matrices, which for us we only use for constraint Jacobians actually, because we don't assemble map stiffness. So, but just to summarize, like the only one step we made, which is still significant, was to unify actually the usage of the compressed sparse format everywhere. So that actually it's easier to convert, even though if it's the storage type is actually blocks for us, it's still quite easy to convert it to a scalar compressed format if it's something that you want to, when you want to interface with an external linear algebra solver library like Eigen or so yeah. That's the only things we addressed, I would say.
Sounds like having
what is the compressed format you use?
I think it's well, it's pretty standard. It's a compressed parse, so it's you have I think it's a 3 or 4 array variant. So you have just either the row or the call pointers for to tell you like what are the indices of the rows. Then you have like another array which basically tells you like for this particular row or this particular column, then there is a set of indices which contains like all the values for that particular
so
row.
It's really standard. It's not a rectangular block.
Then there is like what is stored inside, like the values of the that are stored by the matrix, which can be blocks actually instead of scalars. So if you want to convert, but I remember like I when we did like our proposal like at Insimo, I suggested like or I implemented a linear solver which was basically doing like this conversion to, as an example, like from basically this block storage to I just give me one second. I will just point that back again. Just a second. I put it back here. Right. Sorry, I just put it in the chat. So yeah, but just but it's not a big deal. It's just an example of how you would convert like this compressed storage to which contains well this block sparse matrix into a sparse scalar matrix. So that's
what function we should look at?
Is it the one which is highlighted? I think no. Line
set system eigen.
Same eigen, yeah, from MBK, yeah.
From MBK.
So basically, you feel the same. Well, you have here you have to convert to a scalar matrix, but essentially, like the arrays that are stored by the in the MBK matrix are pretty standard actually. Yeah. For it's the one you find like here it's you only have like 3 arrays to describe like your matrix because it's it has there's entry everywhere since it's the dynamic matrix, so it's supposed to be invertible here. So there is basically there are entries in the diagonal, like there is no no diagonal, no missing entry in the diagonal of that matrix, because it's supposed to be invertible here. So you only need 3 arrays to describe this compressed storage, and for in the general case you need 4. That's sorry, just
but the thing I don't understand, is it for the matrix derive, or is it for the matrix of the system?
yeah, Maxime, exactly. Yeah, it's MKL also supports block sparse. So basically, it's we can exchange pointers like with the MKL library from Intel if you want to use this. Well, just as a reminder, it's some documentation about different types of way of storing with a you have array variation, which is usually typically used for matrix which are invertible, and the 4 array variant, which is used like if for instance, like you have a diagonal entry which is missing, and then you need to explicitly reference like the rows of the matrix. So that's both of these. So yeah, it's pretty standard. And then depending on the if you're storing like row or column major, then the values are, yeah, basically you can exchange columns and with rows, and you have like the compressed column sparse storage. And for as far as yeah, to come back to SOFA terminology, as far as the MBK matrix is concerned, since it's symmetric, you can directly exchange rows and columns. It's the same thing. Iterating on rows or on columns, it's exactly the same result because it's symmetric.
But not always, right?
Say again? Sorry, I think my microphone is terrible. I don't know for what reason, but
yeah, it's some kind of sometimes it's a bit cut. I don't know exactly why either. But sometimes right now it was actually super smooth. But
I think my connection is super jitter. Actually, I don't think it comes from my microphone. I think it's from the connection. Right. Sorry, I just maybe what I'm mentioning is just super trivial for you guys, but it just.
No, but it's something I think we already took a look at those sparse class.
So yeah, maybe we can move to another topic. I mean, something I believe that has already been discussed in the past. So.
We got back to this topic because it was actually quite linked to another. You know, this idea of matrix assembly, and then to use those exact same matrix format for constraints resolution. The idea here was to maybe get the idea of what was the plan for not focus on matrix assembly, but what was the plan of the work of Alex on constraints, and also for that to have also the input of Christian and Alex about the I would say maybe a bit more long-term goal for this constraint approaches. And since you mentioned that you had currently interest in constraints as well, François, I thought maybe it was a good idea to make. So that's why there is this session to make this discussion around constraints, so that it's also the opportunity to chat about possible connections and possible collaboration until the next STC, maybe to start on this topic of constraint. That's why.
No.
Christian?
Oui.
Maybe just getting back quickly to matrix derive. I'm really not used to it. I hit these matrix derive recently by implementing the barycentric mapping. Is it? I mean, could you explain really quickly what does it represent? Because from what I understood, it's a sparse matrix of vector, like a vec3 or vec. What are those vect actually? It's I have difficult time
No,
understanding.
it's a good question. In fact, the idea at the beginning was to say that when you put a Lagrange multiplier, you have a HT matrix multiplied by lambda. Okay, and this HT matrix is basically is often a matrix with a lot of lines, okay, full of zero, but a few columns, the few columns being the number of constraints you have. Okay, and when you multiply the Lagrange multiplier by the column, you are supposed to have, I mean, mathematically, you are supposed to have a vector that has the same size of your system. I mean, it's supposed to be, for instance, a vec derive. Okay, it's a
the
force.
result of.
Yeah. Okay, but so the idea was to say then we should in fact store this matrix derive as a series of columns, you know, that represents the different contribution of the different constraints. That was the idea, but that was the initial idea, and that's can be explained by this Lagrange multiplier usage, but we also realized that we would need to propagate this matrix H through mappings, because
Yeah, exactly.
when you want to create a Lagrange multiplier, I just redo all the story.
No, but
Okay.
it's good.
And that's why we created this apply G T to constraint, so to matrix derive, because the idea was to say, okay, if I have a mapping, I have defined my Lagrange multiplier on a map model, and I want to transfer the matrix into a mapping, I will have to do that. So we started to do some operation that looks like, you know, GT. So matrix of the GT, the matrix of the mapping multiplied by small h, for instance, a matrix of the. And more recently, when we looked at what we need to do if we want to map a matrix under a mapping, in fact, we realized that it was really similar to what is done in this apply GT to matrix derive. But just so we reuse that, but at the end, the more we use that, okay, I think the more the underlying structure, I think, as François mentioned, is efficient. I mean, again, it was coded as a map of map.
Yeah, but it
probably
could be...
it's not the best way of coding that, and in general, I'm not even sure that we should keep this idea of matrix derive, because, you know, these are typically the things that came from a long time, and today, given the usage we do,
Yeah.
I'm thinking maybe, and if we do this effort on matrix assembly of trying to unify the way we assemble matrix, we should do it at the same time. That's why it's linked, I think, for constraints, and if possible, to have the same kind of format used for force field than for constraints. That would be,
But
that's
yeah,
my,
that's why,
at least the same kind of mechanism. Okay.
It's like what Francois showed, like having sparse matrix of blocks. It makes sense. You can find it in most linear algebra libraries, but having a sparse matrix of vector, that was what actually bugged me. It's like a tensor.
It's block of one, and no, but I agree, and the format today it's when you read constraint because it's when you want to debug, sometimes you want to know like when a constraint, for instance, is not working. The first thing you do when you debug is to go to the mechanical object and see if the constraint matrix is filled correctly. At least it's what I do. But to read what is written, what is given to the user, to be honest, you need to. It's because I know how it works, but it's not really straightforward to understand this map of map, and probably we would gain some of course some easy use if we had more standard representation.
But this constraint matrix, if I understood correctly, it could be propagated through the mapping the same way the stiffness is for force field.
So so today what we do is when we want to because the thing is that you can sometimes your force field is not under one mapping but a series of mapping.
Yeah.
Okay, so for every node that has a force field that is mapped, okay, that receives some information from some stiffness and mapping. In fact, we put a matrix derive. So, in fact, with a block of 1, 0, 0, 0, 1, 0, and with an identity block. In fact. So we have 3 columns of a matrix derive, and we propagate that through the mappings, okay, so that we compute, in fact, the transfer between the mapped space and the DOF space. Okay. So that's we did that because it was again this operation apply GT to matrix was implemented. And that was available, so we reused just that. But at the end, when we do that, and we add at the end a matrix derive, and we transform it into a sparse format to do all the multiplication. So
I guess we could.
So for me, there is 2 solutions. In fact, there is either we say, I think it's the same kind of discussion with the matrix assembly. Either we say really we say that now we impose the format of a sparse matrix, or we maybe could still use this matrix derive, but at least change the underlying way it's stored. I think as they did in.
Yeah, and in that case, mappings, we could remove this apply GT with matrix derive.
We cannot really remove. We need to, if we remove, we need to replace because it's useful.
Yeah,
to be able to map.
But we could do it just with get J. I mean, or not get J, but add J to matrix, for example, something like that, similar to what add force is doing to the force field.
Yeah, the only thing which makes the thing a little bit difficult is that and maybe it's we have the same issue with matrix, is that maybe you don't want to build all your G matrix. For instance, imagine that you have a very complex collision model, and at the end you just have one penalty, and you want to have this stiffness on one point projected into your FEM model. Okay, so what today the good thing of apply GT applied to the matrix derive is that you would define a matrix derive in the direction of your spring. Okay, you have one direction, and then this direction is mapped to your collision model, and then to your FEM model. And each time it's mapped, the complexity is linked to the number of DOF you map. Okay, not the size of the mapping, because if you impose to create each time the G matrix of every mapping, it could be very costly. Actually.
Yeah, no, of course, but yeah, we already had this discussion, I think. Yeah, we could keep an apply G to do this multiplication, or we could use a sparse matrix to do this. But
yeah, because I think the conclusion of the other side is actually to say that if we use sparse matrices, making smart enough multiplication, they should immediately trigger that there is only 1, 2, 3 values non-zero, and just drop the rest, and that's it.
Yeah, it's basically you put 0 in your matrix where your DOF are not mapped. Actually,
that's exactly the format that we. It's maybe actually the reason why already last time François shared the CSR format. It's you only store what is non-zero.
I think we lost Hugo.
Ah, really?
No, I can hear you.
You're back. Okay.
Okay, sorry. Maybe. Sorry. I'm gonna close the other computer.
No, it's okay. It was okay for me.
And yeah, and that erased that make already the point of CSR format rising already last time, saying yeah, but with this format we will just focus on the only limited number of operations.
Yeah, and it's for me it will also be simplifying this matrix API, this mapping API. So this apply G to a matrix type is maybe if we can avoid it using a simpler API, it would be great. But,
so what would be your ideal API?
The minimum number of methods to implement in the mapping. So your mapping function and its derivative should be enough, I think. To at least because you have two kind of the mapping is doing two things. It's mapping a position in one direction, and in the other direction it's mapping forces. So you kind of have two function apply and two derivative of these functions.
So at least I agree. But I also remember that at some point, in Grenoble to have only apply and basically Gedgy, they developed this concept of mask, and because they didn't want to do the Gedgy on all the DOF, etc. So the difficulty is there, I think, in the code. The difficulty is to have an interface, but it's a question. How do you see the interface to
I would add
just construct G on demand where it's necessary?
Yeah, I would add this to our cool diagram for matrix assembly, because I think if we are aiming for one way to do it for both force field and mapping, even this would be great because it's simplifying everything. So you like the way you build the vector field or your add force or your apply mapping and getting its derivative. If you at least use the same way in both components, it's maybe simpler for the one who's developing them. But yeah, I would add it to as a complementary part of the matrix assembly discussion. I think they should be together, or at least very, very close, because what you are doing in the mapping will contribute to the system at the end, right?
Yeah, of course.
So we need to take this into account. Especially
I
if you
just
want
had
to
a-
solve in the direct way your constraint. But I'm really not an expert on constraints, so maybe I'm telling nonsense. But I guess if you want to solve your constraint in one step, you need to build a whole system, right? With
Yeah, that's what at the end Alex said about direct or indirect way of doing this something. Today we are using the free motion, so we do the indirect way. So we first compute a version without any constraint, and then we compute the constraint system. You also have people that directly solve the constraint system in one step. This is not something that we often use, but why not opening this opportunity? I mean, if it's possible, and particularly if, again, the stiffness matrix and the constraint matrix are written in a way that is similar, it will help, I think. I don't know if you already do that in Simo, François, like doing a direct solve of matrix of constraint
Constraints
matrix,
for constraint solvers. Yeah.
I implemented like for bilateral. I don't know if that's exactly your question.
Yes.
Only for bilateral constraints.
Bilateral.
Basically, you augment the Koleski factorization of your system based on the bilateral constraints you want to apply to it. So it adds new rows, which are actually matrix derived, like in the if you want to use like a SOFA terminology. So they're rectangular, like the Jacobian of your bilateral constraints, and then you augment your factorization to actually tackle these bilateral constraints together with the dynamics of your system, so that they are not part of the iterative solving in the Gauss-Seidel anymore. So basically, it saves quite a lot of iterations with linear constraints when you do that. But it's not magical. I mean, it's a plus, but it's not. It's good if you have lots of bilateral constraints which are sort of static in your scene, and they sort of describe a constitutive relationship of your model, like for instance, like inextensibility, and in which case
it could be
there's an
used, for
advantage.
instance, for, I think it's useful for, it's something that we are often asked to do, but we never really do, is like if you want to do like volume constraint.
Yeah, volume constraints, they can be described usually with a single line, so they are quite nice.
No, but usually what people avoid to do it at the level of the organ, because then you keep the volume, but you could have transfer volume that are not interesting.
Yeah,
but
I presume
there are technical way of doing that. But at the end, it's useful to use. Like,
yeah, you can enforce like a with Lagrange multiplier. It's typically a good strategy. Yeah, and that could fit with that design. But yeah, that's a
in that
story.
case, you prefer. I think this is the case where, for instance, computing the factorization with this Lagrange multiplier would be interesting.
Yeah, unfortunately we don't have any open source version like to submit for this. For you
No,
guys
but for me, it's just go to the same motivation. It's just that the two subjects are linked. I mean, it's just that what is true for matrix assembly for force field is also true for this.
Matrix, Maxime is telling on the chat that they also do something like similarly to what I described, like at Anatoscope, like augmenting an existing factorization, or is it something entirely different? Or is it...
Yeah, that's what I understood as well, but we'll see if
yeah,
Maxime
I wasn't looking at the chat, so I didn't know when was.
I just noticed that as well. Okay. And Olivier, you wanted to add something as well, right? You're
Can you hear me?
Yeah.
Cool.
There is Maxime and Olivier in the same
Maxime,
time.
yeah. Sorry.
Okay. Go ahead, Maxime, and Olivier.
Okay, yeah.
Thank you.
No, just wanted to mention that we usually solve the whole system, assembled system at Anatoscope. We assemble this gigantic sparse matrix CSR, and we feed that to some solvers like eigen solvers or Gauss-Seidel that we have internally. So it works, but it's pretty slow depending on the size of the system. Of course, matrix assembly is always the bottleneck because systems are huge, but I have no magic solution at this point. Just to mention that it can be done. And we completely skip the matrix derive. Actually, we remove them altogether in our fork. We only use the matrix, the mapping Jacobians. So we assemble like eigen sparse matrix per mapping, and then we concatenate all this chain of mappings all the way down to the constraints, and then we get this huge KKT system that we feed to either like MinRes, LDLT solver, or some external QP solver if we have unilateral constraints. And so yeah, it works, but yeah, it's a lot of bookkeeping to to arrange all this. Yes.
And did you keep the mask thing?
Yeah, the mask is still here. The masks are useful because I don't know. There was this hypothesis that we should be able to do CCD collision detection. So to do CCD, we need to propagate velocities, and most of the time we don't want to implement separately apply G and matrix assembly for the Jacobian of the mappings. So generally we assemble the whole mapping Jacobians just to propagate the velocities all the way to the collision DUFs. And so that we can know, okay, this might have a collision, and then we resolve the collision detection, and then we can activate or disable the mask based on the collision detection. So we need to propagate the velocities first, and for that we need to assemble the matrices as well. So it's yeah, it's a huge pain. We'd like to remove this and to do collision detection based only on position, not on velocity, so that we can first know what are the masks, what exactly is colliding, enable the mask, pull the mask, and then we use the mask when we concatenate all the mappings to assemble this big system. But we still assemble the full matrices because, yeah, this is the sucks, yeah.
I think essentially we never really stumble on that problem is because when we propagate things like top down, it's always dense in our case, or we make the approximation, but it's mostly dense, and that's
yeah.
you don't have to. We never have like a use case where you need to propagate things top down, and you're not interested in having like a dense propagation. So that's.
We do mostly like registration, and so in some cases we don't have that many registration, targets. So in this case, the masks are useful because if we use landmarks, for example, on the top, if you take a leg model, you could put landmarks on the on some interest points, so that you don't have to put attraction constraint on the whole mesh, but only on some specific landmarks. And in this case, we could use landmarks. But in this case, what we generally do is to add just another slice of mapping, just a tiny mapping that maps only the landscapes, and then the whole the matrix multiplication with the sparse matrix format takes care of filtering all the lines we need during the concatenation. But there is still this full matrix assembly at one point. This is not a good thing.
This was your point, I think, Christian, when we already discussed about mask some time ago, and I mean, I think the conclusion was, yeah, going through a mapping would be quite equivalent. If the mapping was super efficient, saying, okay, we just need to find the point of concern and so on, that would be just equivalent to going through a mapping, right? Or am I?
No, in fact, we I don't know if I understand well what you say, but for me, the implementation we have today when we map a point, like I don't know if it's exactly the same case you are talking about, but when we have a landmark map, the fact that we use the matrix derive allows to define in advance what point in fact is mapped and what point of interest. So we define a constraint on this point. We go up, and we know that in fact only this part of the G matrix is interested for us. And so it's another implementation of the mask somehow, but without any definition of mask. But what is the part that is less beautiful, I would say, is that we don't have this get G only thing where you only we need to have a specific implementation of the mapping to take care of mapping a sparse matrix through the mapping. So again, but there are similarities, I think, in the spirit of what we said. We need to do some choice in terms of implementation and try to have something that is like unified. But today, I think for me, on the part where when we mapped a force field through mapping, I'm quite happy about the way we implement that. The only part I don't like so much is the format of this matrix derive, particularly the way they are stored.
Olivier, you wanted to add something? Sorry.
Yeah, no, just related to the, if we remove matrix derive and we use a sparse matrix, so like in the mapping, you have two apply JT. So I was just thinking, so you would remove the one that's applying to the matrix derive, and because you already have one that is being applied to one column, it's like if you apply it to a full matrix, you already have you would have code duplication if you just apply it to each. Basically, it's already kind of implemented in each mapping. If you have applied JT to a sparse vector, in a way, you already have the application of applied JT to a sparse matrix. Oh, I don't know if I'm.
Yeah, you're right. I mean, it's a lot of code duplication between apply JT, apply J, apply JT on the matrix, and so that's why we at Anatoscope we settled on just output the Jacobian and that's it. Yeah. But depending on what you want to do, it's maybe not it's sure there is some code duplication. And regarding this, Adrien's proposal on a previous session was pretty interesting regarding the merging of implementing apply J at the same time emitting the matrix. The Jacobian matrix could be done with this proposal, and it's actually really interesting. I don't know if it would solve all this mask issue, but it would sure solve at least some of the problems related to code duplication in mappings, I think. Because like the mappings.
I'm not sure to understand what proposal you're thinking.
Adrien suggested that the format to assemble the matrices would be simply for the mapping or the force field to emit the blocks somehow, and this block will be fed to some virtual function, and this virtual function can actually implement the matrix vector product instead of just assembling the matrix. So you can have your apply J at a time with the same function. You can do the apply J and assembling the mapping, and also do the apply JT, and probably do the apply JT on the matrix derive, because you have all the matrix blocks, and you can apply the matrix blocks to whatever input you have. the component you would pass to this assembly routine, the virtual the mapping assembly, would do the matrix vector product instead of assembling the actual matrix. So that you would have a single function and you would get all the three. And if you're not happy, if it's not fast enough, then you would of course like implement your own, but you would not have to.
Yeah.
That's the point, I think.
It was the point on the 8K matrix, right? Keeping just one function, computing the whole. In our case, it would be the whole J matrix, right? And here it was K matrix. And either in the assembled case, you would actually really recover K, or in the unbuilt case, you would actually make automatically the matrix vector multiplication.
I think that's the idea. That's how I understood.
Yeah,
it's a pretty cool idea, I think. Yeah.
If it's my question is actually that's why I said that we should look at the code tomorrow. I don't understand really how it works in terms of in more deeply. I don't know. I don't see it.
Yeah, I would like to see it also.
You'd have, I mean, the way I see it is like you would have two derived classes, one that does the actual assembly. You assemble the sparse matrix given the blocks, okay, just like now. But you could have another derived class that instead of assembling the matrix based on the blocks, just performs the matrix vector multiplication based on the blocks. So internally, you would do the matrix vector multiplication. But from the mapping point of view, all you see is like you're emitting some blocks to somebody else, and this somebody else uses the blocks, right? And there is just a single method for emitting the J matrix as a form of blocks, and you're done. You would have apply G, apply GT, and apply JT on a matrix derivatives, I guess. And also you could assemble if you want to, but it would be just this single method to implement for mappings and force field. I think it's yeah, it's not complicated to. You just have to make this block emission function to make them virtual. So you would pay one virtual call per block, but I think it's bearable compared to the benefits, I think. It's something I sure will try in our code base soon.
The day was worth it for finding this idea. Okay.
Yeah.
But let me think. When you do a matrix vector multiplication, you call the block in the same order than when you just assemble the matrix. You need to arrange that. Right?
I think it's the matrix is just the sum of its blocks, right? So it's linear, so it doesn't quite matter.
But
Does it?
But if in the case of a matrix,
If I understood correctly, you don't need it to be compressed when you do just need the blocks. That's it. Is that correct? Or
I think the blocks is only to not to get too much overhead for virtual calls, so that you get, I mean, some reasonable performance.
So just one question is more when you implement, is it the external function that the force field which blocks to give, or is it the function inside get K that like give the blocks?
It was the add function, if I understood correctly.
But in the add you can either it's like the function asks for a specific block. No, it's the opposite. It's the force field that pushes the block.
Yeah.
You push the block.
You push a lot of blocks.
You push the block, and then by pushing the block, you can. Because I see it with a multiplication matrix vector pushing the block. Is it possible to perform a sparse matrix multiplication, like a multiplication of this matrix with a sparse by just also pushing the blocks? Maybe. I think it's more difficult if you have more than one column. I mean, one instead of multiplying by a vector as we do with force field, but if we do in constraints, we we have the block of the mapping, and we have the block of the constraints.
Yeah, maybe not for matrix derivative, then maybe it's not really suitable. I'm not sure. In any case, like you would factor out, apply G, apply JT.
Yeah, this idea of factorization anyway is interesting.
But you still need, I know you have the apply, which does the mapping function.
Yeah.
Yeah.
But
And the apply J.
Yeah, apply J is doing the linearization, but you still have the mapping and the other way around. That like you.
I think you would get the apply JT.
Yeah.
You would still get the apply JT as well if you emit the blocks of the Jacobian. You can compute the push forward and the pullback based on the blocks, I guess.
But
and you can assemble also
function that is nonlinear, and you need it Jacobian, right? In both directions. When you get the force up and when you pull the, so you need 4 function.
Oh, the geometric stiffness, right? The applied DG, DJK.
So you will need this one.
Yeah, of course, yes. But this is not the same level. It's the second order. But for the first order, you would get only one method, I think. Modulo constraints. I'm not sure.
No, the only thing is for apply GT on constraints. For me, instead of pushing the block, you are in fact looking at where the constraints are zero, where they are non-null, and then it's more like you want to know for this constraint that apply on this point. Oh, I need this block. You know, it's more like a pooling operation. You ask the mapping to give a block for this point, not as we do in usually it's you push the block, you say okay. You see what I mean? Maybe that's a different operation, but we could probably have the two systems.
I think it's doable. It's maybe not the most efficient. Only it could be maybe more efficient because, as you said, you know exactly which are the active constraints, and you want to pull only this one.
Yeah.
Whereas the emitting the blocks is pretty blind. Unless you have the mask, but yeah.
And maybe we could just keep the two system in mappings. We could have 2 functions. I mean, it would still be an improvement having a system that push the block of G and one system that pull
constraints.
Okay, it's asking the like specific block. Have a system that gives the specific block of the matrix G on demand. Okay, thank you, Maxime, because it helps me to understand what. What
maybe I got it all wrong. Don't get too excited.
We'll see tomorrow. I don't know if you're here tomorrow morning. We understood perfectly what you said. Adrien.
But hopefully first we'll have access to his code, and hopefully there will be ZQ. I didn't check if he replied. Just I wanted to say, so you mentioned about performance. There was the mention of performance here. It's actually in the title of the session, but we digressed a bit since the beginning. Anyway, I'm just concerned a bit about. It's just a note that when Adrien is talking about performances, it has to be taken really with care because he's most of the cases mentioning GPU performances, and this is something else, right? Which is not in the open core of SOFA, and definitely we cannot compare. When you were saying, it could be computationally demanding, finally to push blocks blindly. That's maybe one of the things that Adrien is completely ignoring, but on purpose, because on GPU things are super efficient. Just parallelized and brutally applied. Just a remark. I just don't want to forget that maybe on performances aspects we might miss something here. On that aspect. All right.
And
ahead,
How
Max.
much time do we have? Oh, yeah, it's pretty
5
late.
minutes left, but go ahead, go ahead. I already set up. Basically, this I think this session is really too linked to the matrix assembly. It's more or less some kind of one single topic that goes all together. Just there is one part about the mapping, and mapping and constraints, and there is the rest of SOFA. I don't know what you think, guys, but it's super related. Sure. So do not hesitate to just what I meant is just say what you want to say, Maxime. There is no
regarding the performance in constraints, it's from my experience, it always boils down to which solver you will get in the end, and this drives the whole system, the whole architecture, because this is going to be your bottleneck, and depending on what it accepts, you will have to arrange your data in a certain layout and a certain fashion, and it's really hard to just say, oh, I want performance in constraint, because what kind of constraint? Is it like bilateral, unilateral, frictional? What kind of solver? Iterative, direct? And depending on this, you will have tremendously different results, and they will shape how you will architecture your system. And it's really, really hard to get something that keeps everyone happy for every use case. It's really, really, really hard. The way I see it is that at this point, there is not a really satisfactory story for unilateral constraint using unassembled solver. So you have to go to use direct solver somehow, or some kind of mix. That's what we use in at Anatoscope, yes, for unilateral constraints that general, not just free contacts. Like we want to be able to put unilateral constraint on any kind of DOF because we want this modularity. Yeah, for when we want to model some different, I don't know, joint limits, box constraints anywhere on different kind of DOFs, like it could be material deformation, degrees of freedom. And this is really difficult to do without using Gauss-Seidel, projected Gauss-Seidel solver. We have elasticity, nonlinear elasticity, so we need to factor out this big matrix. So we cannot really do without assembling this whole system. But if you have, if you're in a situation where you have only bilateral constraints, then maybe you could use, I don't know, MinRes, unassembled MinRes solver, and this changes everything. I mean, you don't have to assemble anything. You could just use old style SOFA, CG style, except you're using MinRes, and this will solve your constraints. You will need some preconditioning, most likely, but I mean, it could work, and those are completely different approaches. And so this is really, the use case is really, really important in this case. Just stating the obvious here, but it does really matter in my experiment.
Maxime, did you have any experience of alternative to projected Gauss-Seidel? Like, have you implemented like I know there is a trend like also like for predicted gradient. I think it was
I did that
created by Tasson, and it looks promising like on paper, but I was wondering if you
it's really hard to do it right, and I did play with it. It was a long time ago. Projective conjugate gradient, but still, I mean, it's difficult without assembling and inverting this matrix on the 1-1 side of the KKT system, like the upper left matrix. And what we use generally is a kind of fixed point solver, somewhere between Jacobi and Gauss-Seidel, that use the full KKT system instead of inverting this block. Sometimes it's faster to solve the whole system instead of factoring the top left block. And it's a tough one.